So I'll go over the exam in a minute. Any questions about anything from last time? I thought it'd be fun to do something easy today, namely the vibrating square drum problem. In fact, I'm going to do a vibrating rectangular drum problem because there's an interesting little thing that we can deduce. Turns out if you have a drum of a certain area, then and it's a rectangle, the lowest sounding drum would be the one that's square of that area. That's a fun thing to see, and we'll be able to see it pretty easily. Let's see. This is the basic mathematical problem. It's the wave equation, which you can deduce by cutting the thing into little rectangles and thinking about the infinitesimal Newton's law, F equals ma. A little bit harder than the string problem, but it's the same idea. Let's see. So it's a little bit of physics to see that it's a wave equation that governs this problem. And that's assuming that it's tightly stretched. This membrane is tightly stretched, like most drums are. And that it's perfect, which is never true, but they can be close to being frictionless and etc. So it's an idealized version of the problem. The real problem is always perhaps even nonlinear and more difficult. But the nonlinear aspect of some of these things, if it's stretched tightly, the effects of that nonlinearity would be small. And so it turns out that this approach is useful, even though it's not exactly physically accurate. And then we're also assumed the thing has been excited somehow, either whacking it with a stick, or maybe if it's like a harpsichord drum, you could poke it down and then yank your finger out really fast. That would be like plucking it. Anyway, the initial shape of the drum is a function given. These would be known and given. And if we were to whack it with a stick, we not only would give it an initial displacement, we maybe would give it an initial velocity. And so the fact that the membrane is pinned down on the rim of the drum, that's the boundary condition. So it doesn't move on the boundary of the drum. I'll call that BC for boundary condition. And these conditions are known as the initial conditions, so I'll call them IC. That's the basic problem. Okay. And of course, we've seen the power of the method of separation of variables, and so that's exactly the approach we're going to take here. And so we're going to look for solutions by the method of separation of variables. Let's try u of x, y, t equals x of x times a function t of y of y times a function t of t. When you plug that into the partial differential equation, let's also take c to be 1. That c turns out to be the speed of propagation. If I whack it with a drumstick and let the waves spread out, that's how fast the waves would move in the square. So let's take c to equal 1 just to make life easier. Then the PDE would be d2 dt squared equals the Laplacian of u. And the Laplacian of u is d2u dx squared plus d2u dy squared. And so in the case where we use these simple functions, the t derivatives would pile onto the t function. So that would be a t double prime. And over here, we would get the x derivatives would pile onto the x function. Y and t would just sit there. And then the y derivatives would pile onto the y function as ordinary derivatives. That's the virtue of this reduction. And that looks like it's a mess, but it turns out if you divide by xyt, you'll get something looking, you'd be partially successful at separating your variables. So let's divide by x times y times t. When you do that, you're left with a t double prime over t on the left. And on the right, you get x double prime over x plus y double prime over y. And so this is very similar to, this is weird because we've got a function of t on the left and then a function of not of t on the right. And how could those possibly be equal? So let's see, a typical thing to do is pick a t naught, let t equal something. You see the right-hand side is constant. And then once you know the right-hand side is constant, you conclude the left-hand side is constant too. So left-hand side equals the same constant. Okay, so let's call that constant something. How about lambda? Constant lambda. Okay, so the t problem is going to be a snap. And in fact, we're going to save the t problem for last. T problem is t double prime minus lambda t equals 0. Same old ODE we've done multiple times. And now let's think about the x and the y problem. That's kind of a weird situation. X and y. We have x double prime over x plus y double prime over y equals lambda. So I purposely left a big space there because I'm going to put this thing on the other side, minus y double prime over y. And now we see I've got a function of x equal to a function of y. And so these two things have to be constant. And now then the constant, I'm going to call that constant a different one. Mu. Okay, so we've got x problems now and y problems. Let's see, the x problem is going to be x double prime minus mu x equals 0, and my y problem is similar but different looking, different constants. So my y problem is going to be, see, I'll put that on the other side, y double prime minus lambda minus mu y equals 0. And the boundary conditions, let's see, if we want these functions, let's think about the BC. That's going to be u of x, y of t. That would be x of x times y of y at time equals 0. I'm sorry, for all time. What am I saying? Oh yeah, times t of t. Let's see, what are the boundary conditions? Sorry. I'll do one of them here. Let's see, one of the boundaries would be when x is equal to a. And the y is going from 0 to b. That would be x of a times y of y times t of t on the right side. Let's see, that's right. Yeah, that's the right side edge. There's going to be one for each edge, but and we want that to be equal to 0. So we want that to be 0. And we don't want the 0 solution, so we don't want these two functions to be 0, because that would just give us the 0 function. We don't want these identically 0. And because of that, we don't want the 0 solution, because we know the 0 solution. We need this x of a to be 0. Okay, and as you do that for each of the edges, you get boundary conditions for these problems up here. Namely, boundary condition x of a is equal to 0. Let's see, we need x of 0 is equal to 0, and x of a is equal to 0. The left endpoint and the right endpoint in the x variable needs to be 0. And for the y problem, it'll be y at 0 is 0, and y of b is 0. Those are very familiar problems. Okay, so the x problem looks the cleanest. Let's just do it. We know that that's just Fourier series. In fact, what is it? It's the Fourier sine series. So we've done all the work already. So let's do the x problem. We know to get non-zero solutions, we know that we need the mu to be something very specific, namely mu sub n. We did this. It's minus n pi squared over a. When we did a string of length L, it was n pi over L. That's a string, kind of like a string of length A. And the solutions we get were xn of x equals sine n pi x over L, over A. Okay, and we got the Fourier sine series that way. So we've done that problem. I'm not going to do it again. Now I can think about the y problem. Let's see, the y problem. We're going to have a bunch of y problems. It's y double prime minus Lambda is a constant we don't know yet, and the mu sub n is the constant, which we do, which is restricted now. With the boundary conditions, with y of 0 equals 0 and y of b equals 0. Well, this is the same as the x problem, and so we know we only get non-zero solutions let's see, what do we need? When lambda minus mu n equals minus n pi over b squared. Oh, let's see. I already have an n there. I'm going to make this an m pi over b squared. Okay. And in that case, and we get solutions, I'll call it y sub m. Let's see. Yes, y sub m of y is sine m pi y over b. Okay. Now we'll solve the t problem. Except the t problem, let's see the. I've got the x, I've got the y, and now I've got to think about the t problem. Is t double prime minus lambda t equals 0, and the lambda is, there it is right there. It's, I put the mu n on the other side. Yeah, there it is. It's minus m pi over b squared plus mu sub n, and mu sub n was, so I get minus m pi over b squared minus n pi over a squared. So I think I'll call that lambda nm. So we don't have to solve it for all lambda. Those lambdas, fortunately, they're negative, and that's the wiggling case. That's sines and cosines. So in fact, let's see. I need to let let's let let's see. That's a negative thing. So I'm going to let lambda sub nm be equal to minus omega nm squared. It's a negative number, strictly negative, so it can be written as something squared. And then the characteristic equation for that ODE, remember, is r squared plus omega nm squared equals 0, and we get omega nm. Oh, I don't want m. Minus. When I take the square root, plus omega n, I'm going to get, right, sorry, I get r equals plus or minus I times omega nm. And so we know the ODE theory, in this case, is that my t solution, it's going to depend on the n and the m. So I'll call it t n m of t is a nm cosine omega t plus b nm sine omega nmt. Where the omega nm is the square root. Let's see, the pi I could take the pi out if I wanted to. I get pi b o. Sorry. M b over pi squared plus m a over pi squared. Sorry, this one's an n. That's what I thought. Let's see, pi, right, what the heck. It's m pi over b squared and n pi over a squared. In a minute, I'm going to take a and b to be pi to make my life easier. Okay, so we get a basic solution. It's a little hairier than what we've gotten before, but it is just, and it depends on two numbers now, nm xyt. The x function was, well, I'll just write it as xn of x times ym of t times t nm of t. Okay, and we found that that's going to be sine n pi x over a times sine m pi x over a b times, this is where the constants would go, a n m cosine omega nmt plus b n m sine omega nmt. And that's a vibrating thing. So if I think I showed you these kind of things in Maple before. That the sine function in x and y here is just a shape, and that other stuff makes it vibrate up and down. And that frequency of that vibration is omega nm. So this thing has a sound frequency. The sound frequency, it's like the overtones of a string, except these are really weird looking numbers involving square roots. The sound frequencies of this motion, so it has a pitch, this is the angular frequency omega nm. So that's the pitch you would hear. So these are like the overtones. And the lowest pitch is when n and m are equal to 1. And that would be the fundamental, that's like the fundamental of the string. That's the fundamental pitch of the drum. That you know, if you whacked it with a stick, that's what you'd hear. But the funny thing is, these overtones, instead of being musical, are discordant with the fundamental pitch. So the last thing to do is to think about the. So this is a basic mode of oscillation, and it turns out that the oscillation is composed of these basic modes of oscillation. It's kind of fascinating. And the solution then is going to be u of x, y, t is a sum. Let's see, I've got my constants a and b in there, so I don't have to multiply my things by constants. It's just going to be the sum as n and m. So n's going to go from 1 to infinity, and m is going to go from 1 to infinity of my basic solutions, u, n, m, x, y, t. And interesting, when you want to solve the initial conditions, the last thing, so let's think about the initial conditions. U of x, y, t, 0 rather, that'll be a sum as n and m go from 1 to infinity. And then you'll get, let's see, if you look at, when I stick in time equals 0, all these sine terms are going to be 0 up there in the right corner. The sine terms are going to be 0, and the cosine terms are going to be 1 in the t functions. And so, in fact, you get what looks like a Fourier series, ANM sine n pi x over a times sine n pi m pi y over b. That's a two-dimensional Fourier sine series. So that's a two-dimensional Fourier sine series. And it turns out that those functions are orthogonal when you integrate over the rectangle. And those coefficients then you determine by, you multiply through by one of them. They're all orthogonal, and so that's how you would isolate what the a and m coefficient has to be. So the two-dimensional Fourier sine series, these basic functions are orthogonal. When you integrate over the rectangle. F times G, the area. And so you can determine the coefficients just like we would for the string problem. And then when you do the other problem, let's see, the other problem is du dt at xy comma 0. Then you get the same kind of sum. Let's see. Well, when you differentiate, I got to go back up and look at that thing. All right, when you differentiate this thing in the square bracket in the upper right corner, the derivative of the cosine would be sine. So those all would be 0. And the derivative of sine, an omega nm comes out. And so it's going to look, and it's going to be a cosine, which is 1 when I stick in t equals 0. So it looks very similar. You're going to get a b here. But the difference is you're going to get an omega nm times b nm. And you get the same old functions here. Sine n pi x over a times sine m pi y over b. What? It's plus, because that was a sine. You differentiate sine, you get cosine. Yeah. And so it's that these are going to be determined. Let's see, we want this to be equal to f of xy. And that determines the a and m's. And we want this to be equal to g of xy. And of course, that determines the b and m's, because the w and omega and m's are, we have a formula for those. And so use orthogonality in exactly the same way to determine what the b and m's have to be. So that's kind of a fascinating problem. And the answer comes out. And I could prove in Maple that it is a reasonable thing that actually does what you would expect it to do. And if I told you that fascinating thing. About those overtones. So, fascinating facts. the overtones of the drum are discordant with the fundamental pitch. And so it's going to sound like noise. Square drums sound like noise, not music. The kettle timpanis, kettle drums, they have a nice pitch because the volume of air underneath them is what's really causing the vibration to be restricted to some reasonable sounding thing. If it was just a membrane with nothing underneath it, no volume of air, it would be noise. So overtones of square drums or rectangular drums are discordant. With the fundamental pitch. The fundamental pitch is the lowest one. That's what you think you hear as a pitch. Fundamental pitch of the drum. The fundamental pitch is omega 1, 1. Let's see, what would that be? Fundamental pitch using omega 1, 1 equals the square root of 1 times pi over a squared plus 1 times pi over b squared. And so it's not a beautiful sound like the vibrating string is, it's noise. That's one fascinating thing. And it's going to be fun to simulate the sound. You could do that with an oscilloscope and add those basic things together in various blends and see what kind of noise you get. Another interesting thing is to think about is, let's say you know the area of the rectangular drum. So here's a question. Which rectangular drum with given area has the lowest pitch? And that's not a hard calculus problem. There's the pitch, that's the frequency of the thing, and the lowest pitch would be the biggest, omega. And if you know that A times B is a constant, capital A, then it's a freshman calculus problem to figure out when it's minimized. Well, the lowest pitch would be maximized omega. It turns out the answer is the square one. When A equals B. A equals B, and A squared equals A. That's a fun thing to think about. And let's see. A famous problem that you might have heard about is, can you hear the shape of a drum? It turns out that a drum of any shape has magic numbers like the omegas. Okay, so we'd have a drum of a weird shape and a membrane stretched by it, and then we have the the wave equation. So d2u dt squared equals c squared times the Laplace operator of u, And it turns out that the eigenfunctions of the Laplacian give you the basic pitches of the overtones. So these are eigenfunctions of the Laplacian. They're functions such that the Laplacian of phi is equal to lambda times phi, and phi on the boundary of omega is 0 on the edges. Those are called the eigenfunctions of the Laplacian. And those lambdas determine the pitches of the overtones. Basically, we found those for the rectangle. So the lambdas determine the overtones, the pitches of the overtones. And so the question is, if you know all the lambdas, can you figure out what the omega is? Do they determine omega? And that was an open question for years and years. And when I was a grad student, Carolyn Gordon finally showed that no, they don't. It was a real bummer. Carolyn. And it was kind of a beautiful example. She actually came up with a genuine drum, a shape. It was a weird shape. You'd never want to have a drum like that. But there were two drums of weird shape that had the same overtones, and she was able to demonstrate that. So Carolyn Gordon showed way back in the 80s. No, 70s. No, it's not true. So there's a whole bunch of interesting questions that arise here. I mean, what do you need to pin down the shape of the drum? For example, the circle is really special. And can you tell if your drum is a circle? That's another question that's more tractable. Fascinating thing is the circular drum problem. The lambdas turn out to be related to zeros of the Bessel functions. And those are pretty special. And so another question is, can you tell if your drum is a circle? Bessel functions are been studied to death because they come up in circular problems. And so another question, can you tell if your drum is circular? So those are really interesting problems. I guess it's called spectral theory, if you want to look it up on Wikipedia, if you have a circular drum. I did want to go over the exam, so I think I'll quit for this stuff today and do that. Is there any last questions about the square drum? I thought I'd do something fun today. Yeah.
On the double infinite series, how do you prove convergence of that so you can differentiate like that?
It's kind of like the vibrating string problem. We took it on faith, and then you get this. I mean, it's like the engineers use these things. They get these formulas, they try them out, and they lead to solutions that work. Now we know the various things, like if the thing is differentiable, then everything converges. So if the F's and G's and everything were nicely differentiable, like multiple times, then we would get genuine smooth solutions, and we could demonstrate that they work. Because we know the Fourier series converge rapidly for smoother and smoother things. So we could make sense out of them. Yeah. We don't get a D'Alembert kind of thing in this case, though, so we're kind of stuck with the series expansion. And so this is a case where you got to do it that way. And minimizing the smoothness assumption is a hard thing that people study to death. Let me go to the solutions that I wrote up here. So let's see, the first problem was very routine. I gave you this function. It's actually, there it is, the graph of the function I gave you was 1 from 0 to pi. So that's that blue dash there is the function I gave you. And part A was to write down the Fourier sine coefficients. And there was a formula for that on the back sheet that we know. It's 2 over pi, integral from 0 to pi of the function, which is just 1 times sine nx. So that's most everybody got that right. It's just write it down and do it. It's just to see if you know what those words mean. Cosine n pi is minus 1 to the n, and that allows you to figure out that it's 4 over pi n when n is odd and 0 when n is even. But if you left it in the form cosine n pi, I gave you credit. But then the next question was, this is how we figured out the relationship between full Fourier series and sine series. We realized that if you take the function and take the odd extension of it from minus pi to pi, and then to take the 2 pi periodic extension of that, then you get what that series converges to on the whole real line. And then you realize that series is the Fourier series, the full Fourier series for that function right there, the odd periodic extension. Okay. And that's how we were able to deduce what sine series do convergence-wise. So the sine series would converge in the smooth places, but at the jumps, the sine series would converge to the midpoint of the jump. So those red dots were an important part of the problem. I didn't make people put those little circles there to indicate that the function's not defined. I mean, the function is the red dot. That's the limit of the series. Okay, that went pretty well, I think. And because that is the full Fourier series for that graphed function right there, it's piecewise smooth, so Parseval identity holds. And so therefore, the sum of the squares, the an terms be 0, so they don't appear in the sum. And Parseval's identity says that would be 1 over 2 pi times the integral of the function squared. Well, the function is plus and minus 1, so when you square it, you get 1. And so that's a very easy integral to calculate. Why do I think the answer is 2? What?
Should be 1 over pi times.
Oh. Yeah, the formula was on the back of the sheet. It's 1 over 2 pi when it's the complex version. Yeah. Answer's 2. And you didn't have to write out the fact that it's a sum of 1 over odd squared. Sum of just writing some bn squared was enough. Question about number 1? Number 2 was to see if you knew this fact that when you're talking about trig polynomials of order n, the best approximation to a function in L2 is the one that comes from the Fourier series. So if the function is even, a Fourier series of order n, if you add it out, wouldn't have any sine terms. Because remember, you need to say here that the sine coefficients are all 0 when a function is odd. And so the nth Fourier series trig polynomial is a very special form of just the cosine terms, where a naught is the average of g, and the ANs are the Fourier cosine coefficients, basically. So that was the important thing to do there. Saying that the best approximation is the Fourier series, and then also noting that the Fourier series has no sine terms was important there. Most people did that. Number 3 was about questions about number 2. Sorry. Number 3 was to see that you understood the basic idea of Fourier series and orthogonal functions. So I gave you these 3 functions, and to see they're orthogonal, there's very minimal computation to do. One was x and cosine 2x on the interval from minus pi to pi. And when you write out the integral for orthogonality, x is odd, cosine is even, so the product is odd, and you're integrating on a symmetric interval, so that integral would be 0. If you didn't say that, then you have to use integration by parts. It's not terribly hard. That's why when I give this as a real problem, I put x to the 11th power there. So it'd be crazy to do it that way. You have to use a reduction formula. Okay, and similarly, x is orthogonal to 1 for the same reason, but that's an easy integral to calculate too. The one that doesn't fall out for obvious reasons is cosine 2x is orthogonal to 1. That integral, they're both even, so the product would be even, and so it's not 0 for symmetric reasons. Some people said, well, it's 1 period, so the integral is 0. That's a true thing about cosine and sine, because the hump above is the same area as the hump below the axis, so they cancel. That's not a very scientific. So it's a false thing to say that 2 pi periodic implies that integral is 0. That's a special thing about sines and cosines. I don't think I took many points off for that mistake, but that's not valid reasoning. So that one you actually have to compute, and it's an easy integral, and it's 0. So you got 3 things to check that are orthogonal, and most people did that nicely. In fact, there were a lot of 100% on this exam. A surprising number. So I was very pleased with how people did. Well, then, this is like what we did when we were developing sine series solutions to the string problem. If we have a function that we want to expand in those 3, then to figure out what those coefficients would be, if that was the case, you multiply by one of the functions and integrate, and that cuts out all the other coefficients except for the 1 associated with that function. So when I multiply by 1 and integrate, I get an integral on the left, and most of the junk on the right is 0 because of orthogonality, except the 1 times 1 function. And so that spits out that. When I do it with x, it isolates the c1 function. And when I do it with cosine 2x, it isolates the c2. And when you collect those, you get those there. You didn't have to calculate those integrals in the denominator. But if you do, that's what you get. Let's see the last one in a few seconds here. R to the n cosine n theta is the real part of a familiar looking thing, namely r to the n cosine n theta plus I sine n theta. And that's e to the I theta to the nth power. And here's where the hint, the Moivre's formula comes in handy. That's r to the e to the I theta to the n. And in polar coordinates, r e to the I theta is x plus I y. So it's the real part of xy to the n. And that's clearly a polynomial. If you wanted to write it out and you just use the binomial theorem,